Welcome to this explainer. Okay, you know that classic game of telephone, right? You whisper a message to the person next to you, they whisper it to the next person, and by the time it reaches the very end of the line, the original message is just completely mangled. Well, frustratingly enough, that is exactly what's happening right now inside the brains of today's most advanced robots. They are essentially playing a high-stakes game of telephone with their own internal systems, and it's causing some seriously clumsy delays and compounded errors. But today, we're going to look at a potential cure for all that. We are breaking down a brand new, frankly fascinating technical report on iFLYTEK-Embodied-Omni. It's a model that completely reimagines how an AI agent actually processes the world around it.
So let's just dive right into this. Here's our quick roadmap for today. We are going to cover the embodied agent bottleneck, the new unified Omni framework, this really cool brain and cerebellum concept, the progressive four-stage training, and finally, we'll wrap up with a developer playbook.
All right, part one, the embodied agent bottleneck, or why compound errors are such a headache in robotics right now.
To really understand why this new solution is such a big deal, we first kind of have to understand the problem with the old way of doing things. Traditionally, these systems use what's called a cascaded pipeline. They're just chaining separate modules together. So step one, a vision language model, or VLM, parses a human instruction. Let's say, pick up the cup. Then, step two, a video generation model, the VGM, takes that parsed instruction and actually synthesizes a predicted visual frame of what the future should look like. And finally, step three, an action generation model, the AGM, looks at that synthetic, generated image and tries to infer the motor controls required to make it happen. Because these are totally separate modules chained together, each step is forced to operate on a degraded, synthetic representation of the last step's output. It's like working off a copy of a copy.
And here is the kicker. Because of that setup, errors inevitably accumulate at every single boundary. I mean, think about it. If the vision language model even slightly misunderstands the prompt, the video generation model is going to synthesize an entirely wrong future state, and then the action model just generates a completely useless physical movement. Plus, this strict serialization creates massive latency. The robot literally has to wait for step one to finish before step two can even start. And the result? You get these really choppy, hesitant physical actions in the real world.
Which brings us to section two, a unified Omni framework. Basically, eliminating those boundaries altogether. The contrast here is just night and day. Instead of that old broken assembly line we just talked about, the iFLYTEK-Embodied-Omni approach uses a single unified framework. By bringing vision, language, and action all under one roof, they communicate through shared multimodal self-attention. What this means is the model learns joint representations where visual features, linguistic instructions, and motor commands are all occupying the exact same attention space. By aligning the gradients and the context across all the modalities, that translation overhead we saw earlier, it just vanishes. The model isn't sitting around waiting for intermediate synthetic images anymore. It is predicting action chunks conditioned directly on the full, raw, multimodal context.
Moving right along to section three, the brain and cerebellum. I absolutely love this biology-inspired architecture. So this unified Omni framework establishes what the report calls brain-cerebellum collaboration. This is a design pattern that separates high-level instruction and planning from the low-level executable action chunks using that shared multimodal context we just discussed. It's actually exactly how human biology works. Your conscious brain decides, hey, I want to catch that ball, right? But it's your cerebellum that automatically calculates the exact micro-level muscle twitches required to actually raise your arm and close your hand. This AI model does the exact same thing, which lets it completely bypass those error-prone intermediate translation steps. This table breaks the whole thing down perfectly. It is a total division of labor. The VLM and VGM, they act as the high-level brain. They're handling the cognitive heavy lifting, understanding the instructions, planning out the task, tracking progress, and predicting those future visual states. Meanwhile, the action generation model functions as the low-level cerebellum. Its one and only job is to take those planned subgoals from the brain, combine them with the shared multimodal context, and directly convert them into executable action chunks. The brain thinks, the cerebellum acts, and it does it all without losing an ounce of fidelity in translation. All right, section four, progressive four-stage training. How do we actually build this thing?
Now, you might be thinking, okay, why not just dump all the training data in at once and let it run? Well, that would actually be a disaster. The training has to be built progressively. Stage 1, you train the VLM. Stage 2, the VGM. Stage 3, the AGM. These individual components absolutely must establish their own modality-specific foundations and stabilize their gradient flows independently first. Only after all of that, in stage 4, do you finally bring them all together to jointly fine-tune the complete model, aligning those shared attention mechanisms across all 3 streams.
Why go through all this trouble, though? Well, this quote right here from the report really hits the nail on the head. Progressive training prevents catastrophic forgetting. If you tried to train everything simultaneously right from scratch, the sheer mathematical weight of learning those low-level motor controls in the cerebellum could literally overwrite and destroy the high-level cognitive planning capabilities forming in the brain. It is an incredibly delicate balancing act.
And to feed this complex 4-stage process, you need a seriously massive, highly specific data cocktail. The researchers combined action-annotated videos from human demonstrations to directly supervise the AGM, robot interaction logs, embodied reasoning datasets, and general-purpose image text data to really expand the model's linguistic and visual priors. But honestly, what I find truly fascinating here is the inclusion of action-free videos. Even without any motor commands attached to them, these regular videos act as a powerful teacher. They allow the model to ground itself visually and actually learn the physics and environmental dynamics of the world just by watching. How cool is that?
Which brings us to our final section, number 5, the developer playbook. What does this actually mean for you? If you are an engineer looking to integrate this unified approach into your own robotic stack, the rules of the game are definitely changing. Here is your actionable playbook based on their findings. First off, you must prioritize datasets that feature aligned vision, language, action triplets. Frame-level action annotations are just non-negotiable if you want cerebellum precision. Second, expect longer initial training cycles and way more upfront compute compared to the old modular training. Third, when you're testing, you need to test inference latency holistically. Sure, you lose the interface bottlenecks, but your per-step computational load increases because of that joint self-attention. And finally, carefully tune your action chunk granularity so that the length of the executable chunks perfectly matches your specific robot's control frequency and safety limits. I want to really zoom in on this specific debugging tip because it's wild. If your shared attention weights get misaligned during that critical fine-tuning phase, it isn't just going to throw a standard error code on your monitor. Because of that direct brain-cerebellum link, this misalignment will physically manifest in the real world as delayed, clumsy, or just completely incorrect action chunk generation from your robot. Your software bug literally becomes a physical hazard. So let's just lay out the grand trade-off you face as a developer today. With traditional modular development on the left, you get the luxury of easily swapping out modules. You can debug things separately, and you use way less upfront compute. But with the unified approach on the right, you lose that easy plug-and-play vibe. You're forced into end-to-end fine-tuning and higher per-step compute. However, the ultimate payoff is a deeply holistic system with drastically reduced interface overhead, which allows the robot to actually act fluidly in the real world. And that leaves us with this massive, industry-wide question. As models like iFLYTEK-Embodied-Omni prove that shared multimodal self-attention can successfully map high-level thought directly to physical action, will unified multimodal foundations make modular AI pipelines entirely obsolete? It is a huge shift in how we think about AI architecture, and it is absolutely something every developer and robotics enthusiast needs to be watching super closely. Thank you so much for joining me for this explainer, and keep exploring.